Okay, so the first lesson we're going to take a look at with parabolas, or rather quadratic functions, is that one we're going to use a vertex form to graph. So to get you thinking about parabolas, we're going to start with a base graph. So this is the plain parabola that, really all we're doing is taking a value and squaring it. We're not really doing anything with it. So maybe just in the corner here we can put a table of values to plot it and see what it looks like. So let's just try a couple of points here like this. That means y is going to be the value squared, so 0, 1, and 4. So I can plot those points right here on my graph, and I can get a couple more, I guess. Let's go -1 and -2. So -1 squared is 1, -2 squared is 4. So I'd be here and here. Now we can connect these dots and try to get a good idea of what a parabola looks like. And I'll do my best to make a good graph. That's not bad. But now that you can see what the parabola looks like, we want to be able to talk about some of the terminology and the language that we'll use to describe it. So the vertex on a parabola is this point right here. Okay, and the vertex here is located at the point 0, 0. And this is one of the most important features on a parabola, and we'll use it a lot, and we'll talk about how to find it in other graphs shortly. The axes of symmetry. So my picture's not the greatest. Maybe I can, you know what, I'm not going to. My picture's not the greatest one to show this to you, but I will use some proper graphing software. But there is some symmetry if we were to cut this parabola right down the middle, and yeah, it does go exactly through the vertex. Now, this symmetry is like looking in a mirror. The distance from here to there is the same as the distance from here to there. And that happens all the way through on this parabola. Everywhere you would go, you'd have the exact same distances, giving you this kind of symmetry. So this axis here, it happens at 0, but we want to be specific about that. It happens when x equals to 0. So that says, that equation x equals 0 basically says y can be anything you want, but x has to equal 0. So that would describe all the values along here where it's symmetric. So I'll just tidy this up a little bit so we can keep using it. So now looking at this graph, does it have a minimum or maximum? What is it? Well, this graph has a minimum, because if you look in the picture, this is the lowest value that it goes down to, but it keeps going on and on and on forever. So because it goes up forever, there's no maximum. It just goes higher and higher. But the minimum, the smallest value, happens down here, and it's at y equals 0. That gives us enough information now to figure out what the range of the graph would be, because if I know what the minimum is and it's going up, that means this graph is going to be greater than or equal to its minimum, which is 0. Okay, so now I'm actually going to go to a graphing calculator. It's a great one online if you haven't tried it. It's Desmos, and we'll take a look at how these things work with some better graphing software. So the first equation that I'm going to write in here is going to look like this, and I will raise that squared, and now it's got this thing here that says add sliders. Do that, and then now we can play around with the values on the graph. So I'm going to start it back where we were at 0, 0, and then we'll see how these sliders affect the values of the graph. So let's look at them one at a time, and let's see what this value of b does here. So if I move b to the right, what's happening to the parabola? It's also moving to the right, and it's moving exactly the amount that b is. So for example, at 3, you can see it's moved itself 3 units to the right. And if I was to back it up this way, say I go to -1, now it's backed it up -1 here on my graph. I'll put it back to where we were, and we'll just record that thought. So b moves the graph left and right. And now we'll take a look at this value of c. So now if I move this one, it's moving it vertically by the same amount. So this one messes with the vertical component of that parabola. And for example, it's exactly what the value of c is. So if the value of c is 2, it's moved itself up by exactly 2. And I can try it with negatives as well. Like go down to -5, and I find that parabola has moved down to -5 as well. So we'll record that thought. The value of c moves the graph up and down. So before we go any further, there's one thing here that's a little peculiar that students have troubles with sometimes, and that's this negative sign here. You'll notice that by putting in the negative, the reason I do that is in this graph I get exactly the value that I use for b. So if I go here to say +3, that's going to show up at +3 here on the x-axis, which is the same value I've used. But if I was to write that in an equation, it would look like this. It would be x minus 3. So that would be y equals x minus 3 squared minus 5, which is the example graph I'm using. So the value for c is exactly as it appears. So it's just -5. And that's what we're seeing here in Desmos is -5. But the trickier part is I'm seeing -3 here, and I'm actually +3 for the value, and the graph has moved 3 to the right. So this does actually move the way we want it, but to get it to use the value of b exactly, we have to do the subtraction. So although I'm seeing -3, it's actually moving the graph 3 to the right in that example. So you have to be careful, because whatever you're seeing is being subtracted. So you're actually going to be using the opposite value. So in this case it would be +3 to tell you where that parabola has gone. Okay, so let's see if we can do this now with a few parabolas. Here's a vertex, and it happens at for this graph. We should talk about how it's been moved. So see if you can tell me what would this graph be moved by, and then I'll tell you what the answer is. So it's 1 to the right, because this would be a +1, and up by 5. So that means the parabola that's been moved, right 1 and up 5, will have a vertex now at 1 and 5. It used to be 0, 0. So when we started it was 0, 0. Now we can find it because we know how the graph moves. Okay, let's try vertex again on this one. So the vertex on this one, how has this one been moved? It's been moved left by 3 and down by 2. So that would mean my vertex is -3 and -2. And in the last one here, I've moved it left by 7, and there's nothing here, so what do? Well, that means it hasn't moved at all. It's in the same place. So -7 and 0. Again, I'll just highlight it one more time. This is -1, but the actual result is a 1. This was +3, but the actual result was -3. +7 and -7. So now we want to find the axes of symmetry. So last time when we started, this is where we were. At x equals 0, we had this nice vertical line that cut the parabola exactly in two. So now if we've moved this graph, where do you think it would show up? And if you think about that axis, you can move the parabola up and down all you want. It's not going to change, right? If I move this up, it's still in the same place. The only way it's going to be affected is if I move the parabola left and right, I have to do the same thing to the axes of symmetry. So if I moved it right 1, that means the axis of symmetry is also 1 over. The other way, of course, that you can locate it is because we know it has to go through the vertex, it's also that x-coordinate on the vertex. So it should be easy then for us to find the axes of symmetry in these. If I move 3 to the left, I have to move the axes of symmetry 3 to the left, and again it goes through the vertex at the same spot. So here it would be at x equals -7. The minimum value on this graph is going to be at, let's see here, the vertex, just like we found last time. So y equals 0, that was the minimum. So this time it's still going to be at the vertex, and that coordinate is 5. So the smallest value it's going to take on is at y equals 5. And again, we started at y equals 0, and we've moved the graph up by 5, so now I'm 5 higher for the minimum value. Started at 0, moved down 2, so the smallest value is going to be -2, which is also the value that goes through the vertex. So again, over here, the minimum value would be 0. So these parabolas are pointing up, which means I know I can find the range now that I have the minimum value. Should be greater than or equal to 5. And y is greater than or equal to -2. Y is greater than or equal to 0. So now that we can hopefully pick out some of these shortcuts from the equation, let's try and graph a couple parabolas. So in this example, you should be able to tell me what's happened to the original. So in this first one, I'll put the original on the graph just to show you what's happened. So here's the original parabola that we started with. This is not the one I'm doing, so maybe I'll use dashed lines to draw this. So the dashed lines is where we started. Now it's going to be moved 2 to the right and down 1. So this vertex here is going to go 2 to the right and down 1. So that's where the vertex is now. Every single point on that graph is going to do the same thing. So that means these 2 points here are going to be 2 to the right and 1 down. 2 to the right and 1 down. And then 2 to the right, 1 down, 2 to the right, and 1 down. So here's the new parabola, and I'll do it in a different color so it's easier to see. Which is again the same graph, but moved 2 units to the right and 1 down. Now, when they take on the same shape, but they've been moved, we call these parabolas congruent. So that's another piece of terminology that we'll need to use for today. That congruent means the parabolas take on the same shape, but they can be moved anywhere on the graphing plane. So same shape, but position can be different. Okay, so now we'll take a look at the next graph. And this graph here has been moved left by 1 and up by 2. So I'll start with the original graph, which looks like this. And again, I'll just put it on a dashed line just as so we have a reference. And I'll put a dashed line here. So if I'm going to move it left by 1 and up by 2, that's the first spot. Left by 1 and up by 2. Left by 1 and up by 2. Left by 1, up by 2. Left by 1, up by 2. Then these are the points on the new parabola in purple. So this is what the new parabola is going to look like. Now, with parabolas, once you can find the vertex, there's a bit of a pattern to it, and I like using this pattern to help me graph quickly. So once I know where the vertex is, which if we knew it went left 1 and up 2, we should know that this is going to be at -1 and 2 for the vertex. So we'd be able to plot this point here right away. Now, I remember the original pattern, which is up here, and the original pattern says when you move 1 over, you go 1 up, 2 over, 4 up, because I'm squaring the values each time. So once I know where the vertex is, the pattern's still repeated. It's just that the vertex has moved. So now when I go over 1, I go up 1 because I've squared it. So this is 1, 1 squared. When I go over 2, then I go up 2, which is up 4, which is 2 squared. And again, if I go over 1, I go up 1 because that's 1 squared. If I go over 2, I go up 4 because that's 2 squared. So if you use this shortcut to graph, and I'll demonstrate it a couple times here coming up, all you need to know is where to start with the vertex. and then you can quickly trace it out that way as well. Both methods will work if you want to start with the original and move it, or if you want to try the shortcut that I just showed. So the last thing that we have to do here is add one more piece to our graph. So we're going to go back to the graphing calculator, and this time I'm going to put an A in the front. And I'll add a slider so that we can play around with what that does as well. So when I move A and I make it bigger, the first thing people tell me is they say, oh, look, it's getting skinnier. And that is true, but that is a side effect of what's really happening to the graph. What's actually happening is it's multiplying vertically. This number here that goes in front, so y equals, and now what it used to be was it was just a 1 when A wasn't there. So when it was just a 1, it would just be the values we had. But now that I'm making A larger, so say I doubled it, that means I'm going to be multiplying by 2 when I put it into the equation. So what I want to show you here is the graphs that we get are actually twice as tall. And if we start back at 1, let's pick a point. And let's move this back to the original just so it's easier for us to see what A does. So the value of A, right now, you can see I'm at 1, 1, then 2, 4, and the same pattern that we normally get applies. And of course, we could go to 3, 9 as well. But watch what happens now if I make A 2. So this time, yes, the graph got skinnier. You can see from the original being here to the new one, which is at 2, it is skinnier. But really what's happened is now I go over 1, and I used to be here. Now I'm twice as tall. If I went over 2, I used to be at 4. Now I'm all the way up at 8, which again is twice as tall. So what I'm going to do is just to compare a couple graphs, I'm going to take the slider off for a second just so that we can compare a couple of graphs where we don't have to move these things. And I'm going to put in, say, y equals x minus 1 squared plus 1. So there's the parabola, and now we're going to compare the exact same one, but I'll put the 2 in front. So now we can see the two graphs at the same time. And again, normally I would go on the blue graph, I would go over 1 and up 1, and I land right there. This time I go over 1, and it's doubled how high up it is. Same thing again here. I go over 2. Over 2 I land there. And I go up 4. So that's the spot where I would be on the blue graph. But the transformed graph, the one I've changed, is all the way up here, which has gone 8 higher. And that's because I've multiplied by 2. We can put in fractions, and it would do the same thing. This time, I go over 1, up 1. It's not 1 higher, it's only a half. Then when I go over 2, it should go up 4, but it's only gone up 2. And again, I would go over 3, and I'd be at 9 higher. And this one here is going to be at 4.5. It's exactly half. So that's the way you want to think about it to make it easier for you to work with, not thinking that it gets skinnier or wider. So let's put our original sliders back in. And this time what I'm going to do is I'm going to move this just a little bit. And watch what happens here when I move A. So this is what we've already been talking about. And we did say that it'll get wider if we go this way. It's going to get really wide. And in fact, if we get to 0, it's no longer a parabola because there's no more x squared term. It's just this flat line. So we don't deal with that case. But now, can you see what's happened as I've gone into negatives? So that's what's different this time, is now that I've pulled up the negatives, you can see that this graph now points down. And that's one big change that we want to record here. So not only does it make the graph, again, we want to think about it as being taller or shorter, it makes the graph point up or down as well. So let's put those thoughts onto paper. So the first thing we've got to record here is if A is a positive, then the parabola will be going up. Otherwise, if A is less than 0, it points down. All right. The other thing we were saying was as the value of, and I'm going to use the absolute value here, as that increases, the graph is stretched vertically. And as the value of A decreases, it's shrunk. Okay, so now let's take the new value of A and see what we can do to apply it to these new parabolas that I have graphed here. So can we still find a vertex? Well, the good news for us is it doesn't change the location of the vertex, because all it does is shrink or stretch the graph. It no longer moves the vertex. So you can see by changing the value of A, I can do whatever I want, but that vertex is still anchored to where it is. These two values still own the vertex. So that means here I'm going right 7 and up 4. So you'll find this at 7 and 4. And here this would be at -3, -5. And here this would be at -1, -8. So that hasn't changed. The axes of symmetry, again, I can change A however I want, and it's still cut right down the middle there. Nothing has changed in that sense. You see the axis of symmetry is not moving. As we said before, the only thing that moves the axes of symmetry is if I change the graph and I move it left and right. That's the only thing that moves the axes of symmetry. So in this instance, if I moved it 7 to the right, that means the axis of symmetry moves 7 to the right as well. And again, it goes through the vertex, so that's where I'm going to find it. So for these, we will see the same pattern. It goes through the vertex. In this case, because it's been moved 3 to the left, so has the axes of symmetry. Okay, this next part is going to change slightly. Do the graphs have a minimum or maximum value? So we need to think about what A does to the graph in order to answer this properly. So in this case, the first graph, we have A greater than 0 here. So because I know it's positive, it's going to be up, which means if the parabola goes like this, it has a minimum, but it goes on forever, so there's no maximum. So it has a minimum value. And again, it's going to be the vertex where we find it, which is at 4. So the vertex moved up 4, so does the minimum value. This time, however, we have a negative value, so the parabola is going to point down. So if you think about the graph we're dealing with here, it's going to look like this, which means if it's pointing down, I have a maximum. It goes down forever, but I do have a maximum here. And again, it's that vertex that we're looking for. So there's a maximum at y equals -5. And in the last graph, again, if we try to use what we've been talking about here, this is a negative. The graph will point down. So if it's pointing down, it's only going to have a maximum. And that will happen when y equals -8, because that's the point that the vertex takes on when it starts pointing down. So again, using this information of minimum and maximum value, I can then tell you what the range is. If it's a minimum, meaning it just gets larger, then it's got to be greater than or equal to 4. But if it's a maximum, that means it has to be smaller than or equal to -5. And if it's a maximum, it has to be less than or equal to -8 here. So let's try to use that information, and we'll graph these parabolas and see how it goes. So I'm going to use that pattern that I talked about in the last graph we did. This one goes right by 3 and it goes up by 1. So the vertex is going to be 3 to the right and up by 1, which is right here. So now that I know what the vertex is, I know that normally this graph will go over 1, up 1, over 1, up 1, over 2, up 4. And I could keep going, but that's enough to get the general picture. So we'll stop here. And remember, this is the original. Right now, I still haven't dealt with that multiplication by 2. So that's what I have to do, is I have to then say, well, it's no longer up 1, it's been doubled. So it's actually going to show up here, which is why I made little faint dots. And then this one has been doubled, so it's not going to show up at this spot here, which is 4 units. It's actually going to go up 8 units, which is going to put it right there. So I can draw the right side of this parabola and repeat this process. Normally I go over 1 and up 1, but because I've doubled it vertically, I will end up over 1, up 2. When I go over 2, I'm normally up 4, but I have to double that. This time I'm up 8. So here's, oops, I can do a better job than that. Here's the transformed graph. So that's, as far as graphing parabolas in vertex form, that's all we have to do. It won't change, but we certainly should practice a little bit here. So why don't we take a look at the next one and see where it would be. This one has been moved left by 1 and up by 18. So that means I've left 1 and 16, 17, 18. And do you notice something different about it this time? If you were to go up, you're going to run out of space pretty quickly because the graph is cut off there. Now, it's not always going to give you that hint, but you should be able to look at this equation now, see that negative, and remind yourself, thank you, I'll restart later, and remind yourself that you're going to be going down with this parabola because it's negative. So normally I would go over 1, down 1, over 1, down 1, and 2 goes down 4, and this one I would go down 4. So this would be my regular parabola, but it has been shrunk vertically by a half. So that means I'm going to put the points halfway from what they used to be. So this was 4, I'm at 2, and this was 1, I'm at a half. So the parabola this time is much wider. I can do better than that. Let's see here. There, that's not bad. So the parabola is going to look roughly like that if we were to graph it. So if you're getting the hang of this, we'll just try a couple questions to see where you're at with parabolas. If you wanted to create a parabola that had only one x-intercept, how would you do that? So it just touches one time, just goes like this and skirts right on the bottom. Well, what that would mean is you're allowed to move the vertex left or right, but not up or down. Because if you move it up or down, you're not going to be on the axes anymore. So we can create any one that we want. Why don't we move it right to the one? Sorry, right one. Or we could move it like 67 to the right. Doesn't matter. Can move it left if you like. Because it's still going to be just touching in one spot when I'm on the axes. Okay. If I want to have two x-intercepts though, that means I have to cross through the graph. So in order to cross through the graph, I could be, say, down here and rising above. That'll work. So I have to move my parabola down. Call it, in this case, it's x plus 2 minus 2. That has two x-intercepts. But really, I can put any number I want in front of here, because even if I start multiplying, the vertex won't move. However I do my vertical stretch or shrink, it's still going to give me two intercepts. So as long as I move my graph below the x-axis, I'm going to have two x-intercepts. And again, it doesn't matter what I put for the stretch or shrink. The vertex is below the x-axis, and going up, it will have two intercepts. The other way, of course, that I could do it is I can move it above. I could go like this and move it above the x-axis, But in order to get to intercepts, that means I'll need to be pointing down like this. So you have to put a negative in front. And again, we can use any number we want. This will have two x-intercepts because I know the vertex is above and it's going down. So the last one you should be able to work out then. If we have no x-intercepts, that means I have to be above the axes and pointing up, something like this. Running out of space here. Let me try like that. It'll never come back down. Or I've got to be below and going down. So in this case, I could try anything like, let's move it below the x-axis and point down. Let's move it above the x-axis and point up. So I could do like 2x plus 1 squared minus, plus 3. So I'm above the x-axis and I'm pointing up. Now that I'm pointing down, I have to be below the x-axis so that I don't touch. Okay, so then the only other thing that you're going to want to be able to do with these graphs is you'll be able to find them from clues. So for example, if I told you this is the graph that I've started with, and I transformed it by moving it 4 units to the right and 8 units down, then you have to be able to figure out what's it going to look like if I do that. So what goes in here and here? If I move 4 units to the right. So one way to think about it is that's 4. So to get back into the equation, it's going to be a negative 4. And to move 8 units down, that's negative 8. So I would just be able to put a negative 8 there. This time, if I want to find an equation that's congruent to 2x squared, that means it has to take on the same shape. So if you want to be congruent, for example, let's try a couple parabolas just to show you which ones are and are not congruent. If I put in y equals 2x squared, y equals 2x squared, and y equals negative 2 x minus 1 squared plus 5, and we'll put one more in here. I'm going to make this a little more exaggerated just so it's easier for you to see. The blue and green graphs are congruent. Even though one's upside down from the other, they take on the same shape. They've just been moved in the space. However, the red graph does not take on the same shape. So the red graph is not congruent to any of the graphs, and the green and the blue are congruent. So the way we know that something's congruent is it has the same stretch value. It might be pointing up or down, but this value here must be the same. So really we're looking at the absolute value of A to be the same in order to make them congruent. So this one, it tells me it's congruent to 2, so I know that the absolute value of A is equal to 2. But remember, that means A is 2 or negative 2. We don't know yet. It gives me some new information. It says I have a maximum value. So what do you know about parabolas with a maximum value? Well, if you have a maximum, it's going to have to be like this, which means the parabola points down. So it could not be 2, it has to be negative 2 in order to have a maximum value. And it tells me it happens at y equals 5, so I know that that's going to be the coordinate of the vertex there for y, and the axis of symmetry is at negative 3. So I know that that's where the vertex must go through at negative 3, 5. So I can reconstruct this equation. And remember, the way it goes in is like this. You subtract the value. So if I simplify it, it would be x plus 3 squared plus 5. Okay, this next one has some clues. It says we have a vertex at 5, negative 1. So right away what we know is we know that we can plug this in as x minus 5 squared minus 1. And I'm still missing this value of A. But this is where I'm going to be able to do when I use the clue they've given me, 7.5. I can then put this in for x and y. So that tells me that 1, which is the y value, equals a times 7 minus 5 squared minus 1. So all I've done is I've put in the x and y values from the point, and I can solve this equation. So if I move my 1 to the other side, 2 is equal to a times 2 squared. So 4a's are equal to 2. So 2 over 4, which is 1/2. So that gives me 1/2 x minus 5 squared minus 1. And maximum value of 12 and x-intercepts. This one you have to think a little bit more about. So let's draw a little picture of it just so we can find it. And it says I've got x-intercepts at -1 and -5 and a maximum value of 12. So somewhere up here, it's not to scale I guess, but this is what my parabola is going to look like. So we have to think about how it got there. So first of all, if you've got the axes of symmetry that you know cuts it right down the middle, that would be very handy to know because then we'd have one of the coordinates here for the vertex. So the middle of these two spots is at -3. And the way you find the middle is if you've got two numbers, you add them together and divide by 2. So -5 plus -1 divided by 2. -6 divided by 2, that's -3. So if you can't see it from the picture you've drawn, that's how you find the middle of two numbers. And if I know this is 12, now actually I know what the vertex is. It's -3, 12. So all that's left is for me to figure out if that's where I have the vertex, what's the value of a? So this is what I have right now. Y equals a times x plus 3 plus 12. So by looking at the picture, I know a has to be negative because it's pointing down. There's a couple ways I can do it. The previous example, we used a point. You have 2 here. You can use the point -1, 0, or you could use the point -5, 0, and you could solve for that value just like we did in the previous example. But I want to give you another strategy just so you see that it is there. And this is what I want you to think about. How far over did we move? This time we moved over 2 in order to get here. So if I moved over by 2, normally I would be going 2 squared, which is 4 high. So this would have to be a 4 if it's the normal graph. However, it's 12, right? It's gone up by 12. So the only way I could have done that is if I tripled it. So 4 times 3 gives me a 12. Therefore, my a value is going to take on triple the vertical stretch. So the absolute value of a is a 3. And as I said, looking at my picture, I can see that it points down. So a must be a -3. So I didn't even need to solve an equation to do it this way. So it can be handy because that process is simpler. I can see that the distance here is 2. So that means to move 2 over, I would normally go 2 squared, which is 4. But this time I did it by 12. The only way I could have done that is if I tripled the vertical stretch. And again, knowing that it moves down, that's why I know it's a negative here for my final answer.